Hi, welcome to Further Matrix Algebra. What is algebra anyway? I guess we've seen it before in a simple way with real numbers letting, I suppose, letters stand in place of numbers. We call them pronumerals, and we can investigate relationships between numbers and working with missing numbers and constructing mathematical sentences or equations. So matrix algebra over here, what could that be? Well, we could perhaps let letters stand for matrices here. We've seen a bit of this before, where we have a bold capital standing for matrices. So, hey, maybe, here's a Huddyism, maybe we'll call these letters pro-matrices, standing for matrices. And there's a couple of expressions here. There's another one with all sorts of funny business going on here. These are, what's a neg1 power of a matrix? We might have to look at that later on. And up here, what's this dude? So we're starting to look at working with matrices in different ways, combining them with perhaps unknown matrices here. There's an unknown matrix with pronumerals in there, x and y. And what are we going to do with that? Well, it's pretty exciting stuff. Here's another big one down here with a -1 power outside. I don't know whether you can raise a matrix to a negative power, can you? Well, let's wait and see what's going to happen here. So come on down. I've taken some screen clipping here from Hayes and Harris again. And we're going to look at what we call the inverse of a 2 by 2 matrix. But let's look at revisiting a pair of equations like this. And we want to try and solve those two equations. You can do that with simultaneous equation. You do it with technology. We have done it with, let's do some revision, an augmented matrix representation to actually solve them simultaneously. And that was back in systems of linear equations. But what about this? Did you realise, now that we have got a product of matrices, that if this row dived down this column, we would generate the expression 2x plus 3y, and it would equal 4. And if this row dived down this column, hey, there's another use for multiplication. Multiplication in matrices, of course, is more than multiplication. It's pairwise multiplication, and then rows diving down columns, and then an addition. So, hey, these little expressions here can be accommodated in matrix land. Bet you didn't think about that. Let's check the solution in here. If we put x is 5 and y is -2 there, and you dive down there it is, the pairwise multiplication and the addition, yes, it does come to 417. So the whole system seems to work. There's another use for matrix multiplication, encoding two equations in a different format. Not the augmented matrix up here, but a product of a matrix with the unknown matrix xy. Interesting stuff. So we've actually created, the ultimate in algebra, is that not so? We've created a mathematical sentence or equation involving pro-matrices, letters standing for matrices. Okay, so the question arises though, how would you solve that? Okay, AX equals B. I know how to do this, mate. Oh, you divide by matrix A. That's not going to work. There is no division by matrices. So it'd be different if it was in pronumeral land, if they were real numbers. X has been times by A. To get X back again, you divide by A. That's all right if they are real numbers, but these letters are standing for matrices. They're pro-matrices. And you can't divide matrices. So how could you work with that sort of equation? And we're going to start with Hayes and Harris approach. Let's imagine there's a matrix C such that when you multiply A by it, you get I. What would happen? Let's multiply in here by C, so you get CAX. Just remember, you've got to multiply on the same side, don't you? Because matrix multiplication is not commutative. So it does matter on which side of this each side of this equation you put your c in. So these two were equal. To keep them equal, we must multiply in the front there, pre-multiply on that side and pre-multiply on this side, because it does matter on which side you multiply, which rows dive down which columns. That's going to be important. Now, if there was such a c, CA has become I. Hey, we've actually solved the equation, not by removing A by division, not by this up here, but by wiping it out as an I, if you like, converting it to I. And IX is just X. So the same idea of isolating X alone, isolate the X, is still being pursued here. But rather than remove the matrix in front, we convert it to I. This is a important difference, of course. Convert A to I by multiplying by our matrix here. So this is same idea, but quite a different approach to doing it in matrix land. Okay, so here, the matrix C, you've got to be able to find one so that when you multiply A by it, converts it to I, and you have isolated your unknown. If it doesn't exist, we can't do it that way. But if it does exist, then we call it, C equals A negative 1. That's what that was. This is doesn't actually mean a power as such. It's a symbol meaning the inverse. That matrix, which will, if you like, undo the multiplication by A. Inverse implies will undo the effect of A. So it converts it to I, maybe. You could call it the multiplicative or multiplication inverse. What's it like? Well, it's like a fraction, isn't it, in real numbers. If you have a real number 2, you want to remove it and make it 1, you multiply it by a half. So that's in real number land, that's the multiplicative inverse. Multiplying by a half converts it to that special number 1, which is the multiplicative identity. And that's what we're doing here, converting A to an identity. So let's come down and develop this a little bit more now. You can see, hey, what are we doing here with boxes of numbers? Had no idea we'd get this interesting. So the multiplication inverse or multiplicative inverse of A, if it exists, it's something which when you multiply by A in either order will give you I, remembering what I is. That matrix which when you multiply by does not change the value or does not change the matrix in any way. It leaves it unchanged. So do you remember that? Or you want to go with a 4 by 4 maybe, just thinking it through. Yeah, can you see the idea of why that leading diagonal there has got to be 1s? They are all examples of the identity matrix. Matrices which, when you multiply any matrix by it, will leave it unchanged. So that's what we're seeking now, is a special one. Here it is. This is going to be called, A neg 1 is called the inverse of A. So it's going to bring it back and nullify it, if you like, make it equal to the identity matrix. All right. How do you do it? How can you find such a thing? Let's make some observations here with Hayes, and Harris. If you get 3, 1, 5, 2 and multiply it by this, look at what's been done. Can you see anything happening here? Can you see this? And then if you multiply it, you get 1, 0, 0, 1. It worked. It gave us I. If you tried this matrix, 1, 2, 3, 4, and did something with these, look at what's been done, and did something with these, look at what's been done. Oh, we almost got I. We got neg 2i. Can you see this little fiddling around here, whatever it is creating zeros in the right spot, and we want that for the identity matrix, but It's actually not dealing with this number and reducing it to 1. Let's do it again. Can you see what's happening? 5, 3. Oh, if we interchange those and then change the sign of the other two, that's what we've been doing, then you get this. Oh, it's a near miss. We got the noughts, but we didn't get ones in there. We got 37 times I. Can you see the pattern? We're interchanging this pair and changing the sign of the other two and almost getting what we want. Sometimes it's working and sometimes it's too big. Let's come down and see if we can investigate that. Okay, so if you look at what we did, here we are, A and D, we interchange those. And then we change the sign of the other two. And when you do that, what do you get? You get AD take BC in those holes, and all these are good. We got the zeros where we want them, but these numbers were too big. So we're going to actually have to divide by AD take BC. So the inverse is actually this thing here. Alright, interchange these two, change the sign of those, and if we divide by AD take BC, we will convert these to ones here. Convert them to ones, not negative 1 there. Convert it to a 1, and that will create I. So then when we multiply A by this much, we will create the 1, 0, 0, 1. We have to reduce the size of it so that we get ones in those positions. Do you get it? Let's come down and look at the definition now. I'll put some calculators there. So I'm going to do it on the calculator as well in a minute. So if that's a matrix, the inverse, that means the matrix when multiplied by A in any order gives I. It's a special wipeout matrix, you might call it. Because when you multiply A by it, it wipes it out to a non-effective matrix in multiplication. It wipes it out and produces I. Okay, so the inverse is divide by this thing and interchange these two to get DA, interchange those two, change the sign of those. It's not really conceptual, this. The idea is that we're trying to construct a matrix which will do this to A up here and create the 1, 0, 0, 1. Okay, now often they want you to do this by hand. Okay, and they could make you do it by hand by putting letters in there as well as numbers. But if you had all numbers, how would you get the calculator to do it? Well, let's come across to this screen here. What have I been doing? Well, I've gone to run mode. I've hit math in run mode. If it's set up as math and not linear, I've hit math, then I've hit mat, and now I have selected a 2 by 2. I could have done a 3 by 3, but I've selected a 2 by 2. I've entered the numbers, and then if I move the cursor across, and that's with this button here, move it across, and then hit hat. Okay, so here's hat here. Hit hat, I'm getting an entry position up here as a power, and then I need to enter -1 and hit execute, and I would have the inverse of that little 2 by 2 matrix. Okay, so you can in run mode find the inverse by treating it just as a power here, fill the box with a -1 power, that will give you the inverse. So you might like to check your work. If you're quick enough, not much point in doing the problem by hand and then doing it with technology every time. It's going to take too long. Okay, so let's go down and have a look at some problems now. Here's the matrix. Find the inverse and solve that. Well, first of all, let's look at our new exciting way of representing a pair of equations. This is the second way now. The augmented matrix was one way. Now we have as a matrix equation. This times this, the rows would dive down the columns and create our two equations. So we've got that. So we've got it in the form AX equals B, if you like. Now, if we could multiply in here by the inverse of that matrix, and what a pre-multiply on the other side as well. Here it is here. What would we convert? Oh, that'd be I. Wipe out. We get x by itself. And then if we did it on this side, there it is. That's the inverse. They're actually sticking the inverse in there now. Can you see it? They've interchanged those two and change the sign of these two and divided by AD take BC, where we're calling this A, B, C, D. AD take BC. Okay. And then if we do that, I suppose you should have checked over here, we maybe should have checked that when we multiply that by this matrix here, we do get I over there. But we've just derived that, so it should be okay. So if you now dive these down here to create these two numbers and then dividing by 1 over -7, and so we get the solution which we were talking about before. Now, the little dude here has got a good point. You have to multiply on the same side of both sides of the equation. So you've got two sides of the equation. If you want to wipe out A, multiplying in here by the inverse, it's got to be in front of the matrix that side as well. It's called pre and post multiplication. So when you're working with both sides of a matrix equation, the multiplication of both sides has to be either both in front or both behind, both pre-multiplying or post-multiplying. Let's have a go. And here's a few little problems for you to develop this new skill. It's an important skill. You can see how useful it is going to be. So I want you to go through and just check these out, build up your skills, converting into matrix equation, that's important. Use matrix algebra, so that means make the equation and then multiply in here by the inverse and so on. Okay, so have a go. Those are the first four, and then we'll just come down to number 5 there, and just have a go, and then I'll take you down to the solutions. So pause it if you want to do that now, and then we'll come down to the solutions. So this is 10E1 from the textbook, and just watching there down to G and H in question 1. We've gone too far there, so just come up. Question 2, 3 and 4, or part of 4. So maybe just come down more slowly now. And 4, A, B, C, see if we can get them all on there. A, B, C. Part of D there. Let's come down and have a look at D. We'll bring up D and E perhaps there. So we've got D and F. Just checking those out. Coming down, there's question 5. Okay, so mark your work and let's keep building on our relationships between matrices and our matrix algebra. So come down to this next example now. And let's have a look at that. Okay, so example 13 from Hayes and Harris. Find the inverse here for the matrix A is 4K 2 neg 1 and state when the inverse exists. So let's look at the inverse. We've got to interchange these two. There they are. Change the sign of the other two and divide by AD, which is neg 4, take BC, which is neg 2K. So when you multiply it all through, we've got that. Now, you can see here, because we're dividing by AD take BC, that can't be 0. Okay, so we could say right back at the beginning, neg 4 take 2K cannot be 0. Okay, so therefore neg 4 can't be equal to 2K and neg 2 cannot be equal to neg 2. So that's an important idea there. Okay, so let's have a look at doing some problems now. Following that solution there, here we have a few here. So 6, 7 and 8. Have a go, just remembering the inverse is not going to exist if AD take BC is naught. That must not be naught for a matrix to have an inverse or be invertible or non-singular. If a matrix hasn't got an inverse, it's said to be singular. Okay, so have a look at those. Let's go down now. Some more here. We'll just go down to the next few. 11 and 12, I think. And then 13. Have a go. Getting interesting now in rearranging expressions and finding inverses. Just learning about what you can do with the inverse. So let's go to the solutions then. There are some solutions for you. Just check those carefully. It's an important area now. And through to 13. So you might just check here. This is going to be important as we go on. The idea of rearranging equations, pre and post multiplying. Okay, so check your work. Let's go on. Okay. So, now we're talking about algebra, so let's write some equations using pro-matrices, letters standing for matrices. That's a Huddyism, it's not usually used, but pro-numerals are letters standing for numbers, so pro-matrices, we're using capital bold letters to stand for matrices. So if we had a matrix equation like this, so this is a matrix equation, isn't it? And it's all unknown matrices, so can we talk about what rules we can apply and what we can do? So it says, using that given information, find the inverse in the linear form RA plus SI. Okay, well, I look at this and I say, hey, I got problems here, mate. There's no inverse in it at all. So how can we find it? Well, let's multiply. There it is. Let's bring it in on the left here because we want to work with it. It's not even there. So I'm pre-multiplying on that side. So I'm going to put it in the same position on the other side. Just remember, pre-multiply. Make sure you're doing it in the same order because a matrix multiplication is not commutative. It does matter which order you're doing it. If you pre-multiply on the left to get in next to the A there, then you've got to do it on the same side of the other side, and that is on the front side, or pre-multiplying. So now if we expand A squared to A by A, the inverse of A neg 1 by A will give us I. And over here, what have we got? Well, we can multiply this out, and we can put the 2 in front because it's a scalar. And then we've got A neg 1 by A, and then multiplying it in here, put the 3 in front, it's a scalar, A neg 1 by I. So, down to IA, and here there's another I, 2I, and here A neg 1 by I is that matrix, which when you multiply by leaves the matrix unchanged, so A neg 1 is there. So now IA is just A, and if we subtract the 2I from that side, we'll have 3A neg 1, and then if we divide both sides by 3. Notice we don't put A over 3 and I or 2I over 3. We don't use that. We use the idea, there isn't a division like that, it's a third of A take 2I. We use the idea of a scalar. So we could do it also like this. So, can you see what I meant by further algebra? We are actually going to work with relationships between matrices in an unknown situation where we don't know the matrix A or B. We're just going to look at rearrangement and expressions involving them. Come down and see how you go. Here are some important ones now. I think you need to look carefully at all of these and just see if you can think your way through. Just remembering that matrix multiplication, you must bundle the terms up in a convenient fashion. So let's write this down. It's the way you bundle the terms up, what bundles you've got. So A by A neg 1 is something you look for. or B by B neg 1. You want the bundles of pairing. The order of the pairs of products is very important, because AB is not equal to BA, and you must squeeze the given information for all you can get. Given info, all must be used. And you've got to be a little bit tricky when you use it. So down in these last few, you might try and play around and be a little bit tricky with how you use this given information. Don't ignore it. All the given information in this particular course must be used to find the solution to the problem. There's no extraneous information provided to sidetrack you. All right, have a go at those. Let's go down and have a look at the solutions. Just come here a little bit. Let's maybe go up just a little bit there. Not too much here, so just coming down. 14A, B and C. Yep. Okay, let's go to 15. Interesting questions there. 16, 17, we'll just capture that a bit better there. Okay. 18 and 19. So they're getting to be a little bit more interesting, those questions. Okay, so check them out. Okay. Let's go on and see if we've got something more to do with this sort of idea in 3x3s. What can we do there? So come down and we'll look at Hayes and Harris talking about, can you do the same sort of thing in 3x3 land? Well, they've done it, haven't they? They've written 3 equations in 3 unknowns, diving down here equals 15, diving down here, yep. That will come out. Just remember, this is an alternative to the augmented matrix idea. 2, 1, 1, 7 is what we did with system of equations before. This is an alternative. So in any test or question, if they say use row operations, they're talking about this. If they're saying use a matrix equation of the form AX equals B, they're talking about this approach. So this is row ops and reduced echelon form, row reduced echelon form, and this is matrix algebra in that. So if you knew the solution, let's just check it. When you dive that down there, do you get the 3 numbers? Yes. So we're going to try and do the same thing. What are we going to try and do? Multiply in here by the inverse and in here. If only we could find now that magical inverse for 3x3s, which does this for us, and, if you like, converts the A to I, and thereby isolating the X there. Okay, let's come down now and see if you can get the hang of getting equations into that form. Okay, so we're just doing a simple multiplication here. This should give I, shouldn't it? And you should check both ways. Check not just that A by B equals I, but B by A must equal I, because an inverse is commutative. It's got to work around both ways. Generally, AB in matrix land is not equal to BA. But when you've got that special matrix, which is the inverse, if that is the inverse there, then it does work both ways around. So check that in question 3. Okay, as we come down here, let's have a look at some more here. 5 and 6 then. And question 7. All right, so this is just warming you up in 3x3 land, getting you interested in the idea of having an inverse matrix there as well. Let's come down and look at the solutions. Okay, so that's 1 through 4. Five and 6. And our final one there, question 7. I hope you're getting excited about these skills. Who would have ever thought boxes of numbers, arrays of numbers, matrices, would have led to these sorts of applications? Quite incredible. Let's go on now. Finding the inverses of 3x3 matrices. How do you do it? We've just checked out the idea back there, but how would you actually find the inverse? The inverse of a 3x3 is not actually in this course as such. So we don't actually have to be able to do it like we do for a 2x2, but you have to be able to get it with technology. So let's have a look. Let's look at this first screen over here. So what have I done? Same as before, gone to run mode and math, and then hit mat, and then entered a 3x3. There it is there, moving the cursor across to the right with this button, same as before, then hitting hat there to get up in this position, and then hitting -1. Same as with the 2x2, wasn't it? We're just entering over here a 3x3. All right, so are you happy with that? You can get it from the calculator, and we don't have to be able to get it by hand. So here it is. Use technology to find the inverse of B, and the answers are right underneath. Just a little bit of calculator practice for you there. Okay, let's go on. And let's look at another example of how we can apply it to 3x3 systems. So here it says using matrix methods and a graphics calculator. So usually they'll say put this in the form AX equals B. Just to clarify what they want you to do with this. So here it is, A by X equals B. So there it is there. What are you going to do? Remember the method, wipe this out, get this by itself by wiping A out, by multiplying by A neg1, and then you'd have I by this, and I by this is just leaving the matrix unchanged. So you've got to do the same thing in there. Because you multiplied in front over on this side, you must multiply in front over on that side. So what was the matrix? From technology, there it is there, and you do the whole thing with technology. That's what they're suggesting. So you've got the inverse and then multiply by, what is this? In mat 3 by 1. You'd enter 3 by 1 next to it, and you could do it all in run mode. All right, very good. Let's have a look at some problems now. So here we are, use matrix methods and technology to solve this. So they mean here AX equals B form, and then use the inverse and solve. Okay, just what we've been doing there before. Okay, so you might have a go at that. And we've got some answers there for 2 and 3 actually. Okay, so mark those. Let's go down now to determinants. Now what's a determinant? Well, we've already seen it, but we didn't use that name. It's this thing here. When you look at finding the inverse of a matrix, you interchange the two here, A and D, change the sign of B, but it ends up too big, doesn't it? So we have to divide by AD, take BC. We call that value AD, take BC the determinant, because it determines whether you can have an inverse. Because it's okay if it comes to a number. If it comes to 0, you can't divide by 0. Cannot divide by 0. So, AD take BC cannot be 0 for an inverse to exist. Okay, so that's we've got what's called a determinant. It determines whether you're going to be able to find the inverse. So if A is invertible, that's one way, it implies it's got an inverse. Or if A is non-singular, that implies it's got an inverse. A is singular means it doesn't have a mate, doesn't have an inverse. Singular implies A neg 1 does not exist. Now that language is not important in this subject, it is important if you're going on with maths. So AD take BC is the crucial dude. It is called the determinant. Very similar idea to B squared take 4AC in quadratic equations, where it's called the discriminant. It discriminates between the sort of solutions you'll get. Are you happy with that? Let's go and have a look at some of those. And we'll just skip a bit. So let's look at Hayes and Harris definition here. If you have a matrix A, B, C, D, the determinant is AD take BC and is denoted by that absolute value or size sort of statement there. And it's got, if A is going to have an inverse, you can't have its determinant equal to naught, what we've just been talking about. So here's an example. Find the determinant. Well, that's A, B, C, D. So it's AD take BC. It comes to 5. So an inverse does exist. Therefore, when you put this system in that form, can you multiply in there by the inverse and in there? Yes, because it exists. Therefore, you will have a unique solution. Notice if you didn't have an inverse, all that means is you can't do this and you won't have a unique solution. But if you can't do it, if you cannot find the inverse, the system may still have infinite solutions. So when determinant of A, or det A as we sometimes call it, when the determinant of A is equal to 0, you can't find the inverse, so that means you can't find a unique solution, but infinite solutions may still be possible. Okay, come on down and let's have a look at some problems, build up the skills again. So here, find the determinant of A, right, so that's a symbol, or we might put det A, are other ways of saying that we're looking at that special value which determines whether we can find an inverse. Okay, just cruise through those, making up equations. Here's one with a K in it, that's interesting. That little stroke in front shouldn't be there, that's a cursor. 2x plus ky equals 8. Okay, go through the process, see it build up there. Okay, let's go down to question 4. Okay, so find some values for the determinant and do a few things with it. Get the determinant of A, square A and then get its determinant, multiply it by 2 and then get its determinant. We're trying to see some patterns there. Are there any patterns in the determinants of those? So you might do most of these problems, I think, to get the hang of it. I'll just go down here to 10 and 11. Okay, some interesting little proofs here, generally not asked in this course, but really interesting to get your head around it. All right, let's go and look at the solutions to those. Okay, so we've got 6 of them there. They are only the solutions, and then down below here, let's just check that. I think we've only got the solutions for the first 6 there in that set. Okay. Let's go on and have a look at the summary of the properties, something you're supposed to get from before, from what you've just done. If you have the determinant of a product, it's equal to the two separate determinants multiplied, and the determinant of a scalar times the matrix is, this is interesting, k squared by a, and the determinant by the determinant of a. And here the determinant of the inverse is 1 over the determinant. I think we showed that one. This one's interesting, but you can see how it comes about, because if you multiply all the entries there, then you want the determinant of that, then it equals Ka by Kd, AD take BC minus KB take KC, and that times there, sorry, K squared AD take K squared BC, which is, yep, K squared lots of the determinant. Okay, so that's a little proof of what we were supposed to be investigating before. Okay, so there are determinant properties there. Let's have a look at the determinant properties of 3x3s. Now, 3x3s are quite complicated. Now, you are expected to do this. You're expected to be able to find the determinant in this course to find whether the system of equations, for example, has a unique solution, but you don't actually have to find the inverse by hand. So this, to get the determinant here for a 3x3, there's our 3x3, this is our rule. So these are called cofactor, 2x2 cofactor matrices, because they are found within the original matrix. How are we going to remember this? How to get the determinant? Well, in a 3x3, that is the value you have to divide by to make those entries 1. We're not going to go into how to do that whole inverse process, but we must get this. Let's have a look at this. We want A1, that number, multiplied by this matrix, the determinant of this matrix in here. That's what that's saying. Get A1 by the determinant of the matrix in there. So you can think of covering up that row and that column and plucking those two out. Then the next one is a bit different. The next one is B1, so let's scrub that out. The next one is we want this value, so forget those perhaps, and oops, sorry, I've done that incorrectly, not that one. This one, the row and the column containing B1, and then we want to multiply it by, that's a little bit different. What we want is C2, A2 and C3, A3. Oh, that's hard to think about. C2, A3, so that's going back the other way. Do you want to do that? So with B1, then it's the other way around. C2, A3 take A2, C3. Some people like to think, well, the second one is problematical, so I'll put a negative in there, but keep this order as it is. So neg B1 and A2, C3 take C2, A3. So you need to make a choice. Will you put B1 like this up here, and then reverse, so C2, A3 take A2, C3, reverse order, or put minus B1 and leave it as the order is here? Okay, we'll practice that again in a minute. And then the last one, let's scrub all this out. The last one is C1 by the determinant of its cofactor matrix, which is this in here. So it's plus C1, and then that's just as it is, A2, B2, A3, B3. That matrix is kept preserved there. So the only problem one is this middle one, whether you put the B1 and then reverse the products in here, or whether you put a negative and keep the matrix as it is. All right, so let's go and have a look at this then. What are we going to do? We want the determinant of A for this 3 by 3. Let's do it. Let's put 1 in front and multiply by the determinant of its cofactor matrix, which is that there. So always put this working line. That's very, very important. Okay, then let's do the next entry. Hang on, we'll just get that right. The next entry is the 2. So there's the 2. And we rule that through, and it's 2 by. Now, it usually is 2 by 2 minus 1 by 3. Now, you've got to remember to do it the other way around. So you put 1 and 3 there, and 2 and 2 in the other holes. So you switch these. Okay, you switch them around. Okay, so do you want to do that? That's one way of doing it. I'll do it another way in a minute. And so the second term is the problem term, and then it's 4, which is that 4, by its cofactor matrix. No funny business there, you just can't find the determinant as it is. So then, working the determinant of this one out, 0 by 2 is 0. Take, that's AD, take BC, which is -1. And then 2 by 3, take 4. And then 4 by -2, take 0. And we can do those and come to -9. Now, most students actually find it's easier to write this. Okay, 1, and that's just covering up the rows and columns. So let's just check that. So do it all again. So we want this one by its cofactor matrix, which is straight there. Okay, plus, now move across the top row to the 2. We have a 2 there, so it's plus 2. We strike through these lines. Its cofactor matrix as it stands is that. Don't touch it. But instead, because that middle term has got a reverse sign, put a minus there. Okay, I think that's easier than switching these terms. So this is 2, 1, 3, 2. Okay, so the negative is instead of switching the terms there from left to right, and then the last one, same process. Here it is, you want a 4, and ruler through the row and the column, and 4 times the determinant of its cofactor matrix through 0, 3, -1. And it will still come to the same thing. This will be 0, take -1. Now we've got a 2 negative in front. And so when we do this, it will be 4, AD take BC, 4 take 3, plus 4 by AD, -2 take 0. It's going to be 1 by 1, take here 2, take 8. And so still going to be -9. Okay. All right. Well, that's interesting. Yep, that's -9. All right, that's interesting here. Can you see the difference? It's still coming to -2. They have done it with reversing the order of the items or the entries in that middle one. We've done it over here by keeping the order the same, but putting a negative in there. All right, so you need to choose which way you're going to handle the second term in here. Okay, we'll come and practice that in a minute. Let's have a look at using the calculator to work out the determinant. If they're all numbers, you can enter it. If you have letters in your 3 by 3, you're going to have to do it by hand, and I want you to show that in some problems. All right, let's have a look at the determinant using technology. So the first thing, what have I done to get this window? Well, what we've done there is to hit options there in run mode to get this window here, options. Okay, with that window now, we're going to hit F2, which chooses mat. And if we choose mat, at this stage, we're going to get these possibilities. That will recall a matrix from storage, We have various other items here, transform, augmented matrix, but we want the determinant, this one here, so we need to hit F3 and it brings up det. Now, we need to go right back to the original math run screen, so we have to hit exit twice. Hit exit, exit, and we come back to this original math mode of run where we had math here and mat there. So now what do? We want to hit math, so you'll hit F4. So if you hit F4, you get the traditional window here, which has got that math in it. So if you now hit mat, so that is using F1. So if we hit F1 there, we will come to this window. Okay, so in this window then we need to choose what? We'll choose a 3 by 3. In here, 3 by 3. And we have that determinant of a 3 by 3 which we can now enter our values into. So you might have a look at that on your calculator. All right, and you can play with that. Let's go down now and have a look at what we need to know about the determinant of 3 by 3. If you have a 3 by 3 system and you put in that form, it's going to have a unique solution, again, as long as you can multiply in there by the inverse. And as with the 2 by 2, we don't do the maths of this. As with the 2 by 2, the determinant of the 3 by 3 cannot be 0. If the determinant of the 3 by 3 is 0, then you cannot find an inverse. And if you cannot find an inverse, it will not have a unique solution. Just remember, if the determinant of the matrix is 0, it implies no inverse, which implies no unique solution, but not no solutions. No unique solution may still have infinite solutions. Infinite solutions are still possible. May have infinite solutions. All right. Let's go and find some determinants of a 3 by 3, and that will bring us to the close on matrix algebra. Now let's have a look, 10G2. So there we have it all. Some problems there. Evaluate. Now, evaluate without technology and with technology. I do a few by hand to make sure you've got the hang of it, particularly that second term. Then the sum of the determinants of the cofactor matrices, and then use technology to check it. All right, so pause the presentation, have a go. Let's go down to a few more, down to question 6. And then question 7. And let's have a look at some answers. If we can get all of question 1 on there. Question 2, 3 and 4 there. 5. Come on to 6 and 7. See if we can get them all on there together. Yep, question 6 and 7. Now, in this course, that's all we're going to do with matrices. So you've come a long way, interesting, from just arrays of numbers to the sorts of things we can develop in the theory of matrices. So that's all for me from now in matrix land, but I'll catch you in a later presentation. Cheers for now.